So our next topic is inverse relations. So let's start with an application. The following formula converts degrees Celsius to Fahrenheit. What if I wanted a formula to convert Fahrenheit to Celsius? What I would need to do is isolate the above equation for C. So our first step is to minus 32 from both sides of the equation. Next step, we can multiply both sides by 5. And finally, we can divide both sides by 9. And what I now have is a formula that converts Fahrenheit to Celsius. So these formulas are what we call the inverse of each other. The one converts Celsius to Fahrenheit, and the other one converts Fahrenheit to Celsius. So if I took 30 degrees Celsius and subbed it into the first formula, I would get out 86 degrees Fahrenheit. So Fahrenheit equals 9 over 5. If I times that by 30 and add 32, that's going to give me 54 plus 32, which equals 86 Fahrenheit. So you see this relationship here takes in degrees Celsius and spits out Fahrenheit. If I took 86 Fahrenheit and subbed it into our new equation for Celsius, so I get Celsius equals 5 over 9. 86 minus 32 is 5 over 9 times 54. This would equal 30 degrees Celsius. So we see how these are inverse relations. The first one takes 30 degrees Celsius and spits out 86 and gives us 86 degrees Fahrenheit. And the inverse function, or inverse relation, we can sub in 86 Fahrenheit and it outputs 30 degrees Celsius. So let's look at it in terms of functions. So if I have f of x equals 2x minus 3, if I sub in 2 to this function, so f at 2, I get 2 times 2 minus 3, which gives me 1. So the input of function f is 2, and out comes the number 1. So function f converts 2 into 1. If I take the next x value there, 5, so f at 5 gives me an output of 7. 2 times 5 is 10, minus 3 is 7. And we see that if I put 5 into my function, 5 gives us the number 7. So what does that mean in terms of the inverse? The inverse works the opposite way. It would take the number 1 and spit out the number 2. It would take the number 7 and give me the number 5. That would be the inverse. F inverse of 1 is going to give me 2, following the arrow, the green arrow. And F inverse of 7 is going to give me 5. Next thing to note is domain and range. The domain of a function is the range of its inverse. So we see the domain of f of x is the range of the inverse. The range of the function is the domain of the inverse, or if you want to say the domain of the inverse is the range of the original function. So let's take a look at how to solve these algebraically. So if I want to determine the inverse of f of x is equal to 2x minus 3, same as our Celsius to Fahrenheit, Fahrenheit to Celsius formula, I need to isolate for the second variable. So I need to isolate for x. I would recommend you change the f of x into a y. So we get y equals 2x minus 3, and then isolate for x. So first step, add 3 to both sides. So I get y plus 3 is equal to 2x. And then divide both sides by 2. So I get y plus 3 over 2 is equal to x. So this is what we call the inverse. Now in a lot of books they switch the x and the y, but that doesn't make sense. We don't switch it unless there's a reason for it to be switched. If it asks for the inverse, this is the inverse. Let's go back to our first example. Again, look at the two formulas that we have. We have this one here and this one here. I'm not switching the Celsius and Fahrenheit. I'm keeping them where they're located. However, if the question asks for f minus 1 or f inverse, this is when we switch the x and the y. So what that means is we take this equation here, we're going to switch the x and the y. So we're going to x plus 3 over 2 is equal to y. And then we write it using function notation. So this means that f inverse of x is equal to x plus 3 over 2. And we only do this for functions. It doesn't make sense if we do it for formulas. Formulas, we don't want to switch the variables. The variables are what the variables are. And the only reason why we might want to do this is to graph the inverse and its function on the same grid. So again, I noted down here, we only replace the y with x when we are required to do so. And the only two reasons why we would do that is when the question asks for f minus 1 of x, or f inverse, or the question asks to graph f of x and its inverse on the same set of axes. So then we need to switch x and y. So let's go to the next example. So how do we do this graphically? So we showed you how to do it algebraically. Let's talk about graphically. If I want to graph y equals 2x minus 3, remember the 2 there is what we call the slope of the line, and this is called the y-intercept. So the y-intercept tells us we start at negative 3, and the slope tells us we go up 2 and over 1. So let's get a couple of points here. If I want to graph the inverse on the same grid, this is where we switch the x and the y. So let's take the 3 points that we just graphed. So we have 0 and negative 3, 1 and negative 1, and 2 and positive 1. If I want to graph the inverse, this is where I switch the x and the y. So now I plot those 3 points. So negative 3 and 0, negative 1 and 1, and 1 and positive 2. So this is f minus 1 of x. A good way to check that if you had this right, so that point of intersection we notice is 3 and 3. And if we switch 3 and 3, we get back 3 and 3. So we know we've at least graphed these correctly. If it was a point that was 3 and 2 and they intersected, it wouldn't make sense. The inverse and its function only intersect at points that have the same x and same y value. For inverses in the graphs, we say they are reflected in y equals x. If I draw the line y equals x, so this is the line y equals x. If I was to fold that grid along that blue line, both those graphs would be right on top of each other. But most important is to realize that if you want to graph the inverse, we're going to switch the x and y values. So let's go through a few more examples. Example 1. Graph the inverse for the given function. So if it's a function you haven't seen before, just take out the key points. So here are the 4 key points of f of x. So the first point is negative 4 and 0. So the inverse would be 0 and negative 4. So I'm translating that first point. The next point we see there is negative 2 and 3. So 3 and negative 2 is going to be our next point. Then we have 0, 2, so 2 and 0. And finally 7 and 4, so we're going to have 4 and 7. So if we connect these points together, again, here is our inverse. So this is f minus 1 of x. Notice we draw the line y equals x. If we fold that graph along the blue line, both images would be right on top of each other. All right, so we've graphed the inverse. Let's state the domain and range. So let's start with the function. So f of x, the domain of f of x is that x can be any real number, but there's a restriction on it. If we look at the x values that can go into the blue graph, we see they start at -4 and go all the way up to 7. So we say -4, x is greater than or equal to -4, but less than or equal to +7. So there is our domain. Let's look at the range. Y is any real number. And then looking at the lowest to highest point on the blue graph, we see that the lowest value is 0 for y, and the highest value is 4. So again, looking at the graph, here are my x values going across this way. That's -4 to 7. And here are my y values going up this way. That goes from 0 to 4. Now let's look at the inverse, so f inverse of x. F inverse of x, if you look at the domain, so x is in the real. So the domain are all the x values that it can take. So if we look at the width of this graph, here it is here. It can take x values from 0 to 4. The range of the original function is the domain of the inverse, which makes sense because we're switching x and y. So next is the range. So y is an element of the real numbers. And we can see that y, the lowest value, is -4, and it goes all the way up to 7. And now we see that the range of the inverse is the domain of the function. So if you know the domain and range of the function or the inverse, then you know the domain or range of the inverse or the function. Part C, is f of x a function? Is f inverse a function? So our definition of a function is that for every x value, there's only one y value. And to check that, we can do what's called the vertical line test. If I take a vertical line and move it horizontally, there should only be one point that hits that green line. So on the blue graph, we see that this is true. F of x is a function, since for every x value, there is only one y value. Now let's look at the inverse. Hopefully you see it at the inverse at a particular spot here. So starting, let's say, here. Notice if I draw a vertical line here, that hits the inverse at 3 points. 1, 2, 3. So for that x value, there are 3 outputs, which means this is not a function. And you can see at some locations there's 1, some 2, and some 3. So if I drew a vertical line here, we can see there's 2 points where it intersects. 1 here, there's 1. From here to here, there's 3. And then again to 2. So this right here is where we have a problem. There's multiple times that a vertical line will hit that red graph. So f of x is not a function. And we see this in between 2 and 3, that the vertical line test fails. Let's go to our next example. So given f of x equals 2x minus 3 squared plus 4, let's graph f of x and graph the inverse of f of x. Let's start with our table of values. So remember, this is a quadratic. And our base table is -2, 1, 0, 1, and 2. And the y values are 4, 1, 0, 1, and 4. And then if we want to transform these, so we're going to take our x, y values, and we're going to transform them using the following formula. There's k values 1, so all I have to do with the x values is add 3. That is the p value. And for the y values, I'm going to do 2 times y plus 4. So let's get our x and y values. And let's graph our transformed function. So there is our graph of f of x. If I want to get the inverse of f of x, all I need to do is switch the points. So if I want f inverse of x, I'm going to have 12 and 1, 6 and 2, 4 and 3, 6 and 4, and 12 and 5. So there is f inverse of x. So is f of x a function? Is f inverse a function? But again, we see that f inverse is not a function. It fails the vertical line test at multiple points. And you notice except at x equals 4. At x equals 4, it has only one output. So here's a question you can think about. What restrictions can you place on f of x so that f inverse is a function? So if you look at the graph of f of x, it has two pieces to it if you want to imagine. So there's this right side here, and there's this left side here. So when we want to state a restriction, we want to get the maximum amount of graph that we can. So for example, if I take the left side of the graph and look at the points, it's going to give me this right here, which is now a function. The bottom half of that parabola there in yellow is the same as the left side of the original function. And similarly, if I take the right side is going to be this top half. So if we want to make a restriction, we're going to look at the vertex for this restriction. So if we split the parabola down the middle, so this is at x equals 3, and we take the left or the right side, we can restrict this parabola, say only draw half of it, and that will give me an inverse, which is also a function. So what restrictions can you place? Here are our two options. We can restrict f of x on x less than or equal to 3, or we can do x greater than or equal to 3. So if we choose the less than or equal to 3, just to remind you what the graph would look like, so let's draw them. If we choose the less than or equal to 3, that's this half of the parabola, and that'll give you this inverse here. If we choose x greater than 3, that would be this half of the parabola, which would give you this inverse right here. So this would be your function, this would be your inverse. Again, this would be your function, this would be your inverse. We can also determine the equation of this graph here. So this is the last part. We can find the equation of this parabola here, and we can do that by isolating for x in our original function. So our original function was y equals 2 x minus 3 squared plus 4. So let's isolate for x. First thing, let's minus 4 from both sides. So minus 4 equals 2 x minus 3 squared. Next, divide both sides by 2. So y minus 4 over 2 equals x minus 3 squared. Next step, we're going to have to square root both sides. Just remember, when you square root both sides of an equation, you're going to have a plus or a minus here. And the last step is to add 3. So I'm going to get x is equal to plus or minus the square root. I'm just going to bring the 1/2 to the front. 1/2 y minus 4, and then plus 3. Notice what we have here is two square root functions. And the last step, since we're talking about the inverse, we're going to switch the x and the y. So we're going to get f inverse of x is equal to plus or minus 1/2 x minus 4 plus 3. So this is the last part. We switch x and y because we want to graph them on the same grid. Notice there are two functions here again, like I said. There's a plus and a minus square root function. So the first function, f inverse of x, could be the positive version with a k value, with a p value, and a q value. And we have the negative version, negative 1/2 x minus 4 plus 3. So which ones do they represent in terms of the graph? Well, the positive one is always the upper part. So if we have a square root function, remember a positive square root looks like this. So this is the graph that has the restriction on f of x. This is true if x is greater than or equal to 3 for f of x. So remember up here we said if x is greater than or equal to 3, that is the positive square root. So there is the equation for it. And similarly for the next one, we get f if x is less than or equal to 3 for f of x, we get the bottom half, or the negative square root. So that is what that function represents, and we see that right here. There's the negative square root. There's the positive. Last example. Let's say you're given the function f of x equals sine x. What restrictions can you place on f of x to make f inverse a function? So let's first take a look at sine of x. Our base graph for sine is 0, 90, 180, 270, and 360. And the outputs for that are 0, 1, 0, negative 1, and 0. So let's graph sine. So there's one cycle of the sine function. And if I want to graph its inverse, if I want to get the inverse of sine, remember we're going to switch the x and y values. So that still remains at 0, 0, but we're going to get 1 and 90, 0 and 180, negative 1 and 270, and 0 and 360. Notice I don't want to plot them on the same grid because it won't fit. So let's plot these points. And here is the inverse sine, what it looks like. Notice the inverse of sine is definitely not a function. However, we could restrict the original graph to make this a function. And we want to maximize or get the biggest function we can out of it. And there's two ways to do this, but this way I find the best is restrict it so we end up with just this portion here, which will pass the vertical line test. So imagine I just want to draw this part right here and ignore the rest. Well, if I look at the original function, that would be this part right here. So if I say only graph from 90 to 270, it will make sure that the inverse is also a function. So for this one, we want to restrict f of x on the interval 90 to 270. And this will ensure that f inverse is a function. So this would be gone, and we'd be left with this graph right here, which passes the vertical line test. All right, so there are some questions from your textbook to try. Notice that 13D, the best way to find the points of intersection is to use graphing technology, and I would recommend just using Desmos to graph the two curves to see where they intersect. And then similar to the one we just did, given that f of x equals cosine x, what restrictions can you place on the function so that f inverse is also a function? That one I'd like you to try as well.